Thank you. And also, of course, thanks to the organizers. I actually love this conference. So I think it's important that we introduce ourselves first and what's our expertise. So I am a theorist and I'm a quantum optician. I work with hybrid quantum systems. And recently, in the last years, I've started working with magnons, okay? And so today, more generally than like matter interfaces, what I want to share with you is our team's ongoing journey to figure out whether and how can we harness the magnon properties for better controlling hybrid quantum systems. And so, again, in the spirit of connecting communities, I think it's very useful that I start by sharing how a person like me sees a magnonic system. Okay, so when we listen about magnons and we see all these wonderful results that have been shown in this conference, and we listen about spin waves. So what do we really see? Okay, how do we really see this system? So yeah, it's a model quantum optician looking at this very complicated, it's a very complicated phenomenology in these magnets. We have some magnetization waves, but what we see in the end, okay, we see just waves, okay? This is our simplistic picture, which have very nice properties, okay, or very curious properties that are very difficult to kind of get in other systems, especially if you have the photonic mindset. So some of these properties that I think are very suggestive are, so magnons have very complex dispersion relations, so relation between frequency and wave number is usually much more involved than in photonic structures, and they are tunable, so I can really move this magnetic field up and down, and my dispersion will go up and down, something that, again, is not so easy to do with photons. Magnons can be in the gigahertz regime, which is very nice because there's a lot of quantum systems that we like that work with these frequencies, but they also can have very short wavelengths as compared to a photon in the gigahertz regime, which means that we don't have potentially this problem of scaling up a system where typical dimensions have to be in like the millimeter range. And also they have kind of like a strong linearity as compared to photons, which is, again, very good because nonlinearity is the quantum resource that we might harness. Of course, and this is very important, I want really to emphasize it, we also see the elephant in the room for us, okay, and is that magnons are really lossy, okay? This has been talked about in this conference, and for a person of my background at least, the losses of magnons are so high as to almost be a deal breaker, okay? I just want to convince, to warn you about this. And so still, it's not the first time that we, in the hybrid quantum systems world, it's not the first time we have worked with lossy systems. So the question I'm trying to answer for myself is whether these high losses is a price we are willing to pay in exchange for what we can do with these properties, okay? So that's our summary on magnonics. So basically what I want to figure out is how useful can spin waves be in terms of hybrid quantum systems, and basically I want to draw this map. Okay, so we have now some very good understanding of classical magnonics. We also have some understanding of quantum magnonics, but I really want to draw a comparison with something that is very well known to me and something that has worked very well, which is how we have managed to go from classical incoherent light to these fantastic quantum optical platforms that we have. Okay, so I want to really try to see if we can draw the analogy, because then I will be satisfied personally with using magnons for hybrid platforms. And so to do so, I have my very personal set of milestones that I consider important and that have been allowing this transition for photons, for light. These are, for instance, classical coherent control of waves. How can I route spin waves across complex circuits? How sensitive can I detect? Is it very important? Okay, can I detect at the single magnon level? Is this necessary, this resolution? Which is the necessary resolution? We don't know, or I do not know. Can we use spin waves to mediate coupling between qubits? Can we really, do some nanostructure engineering to suppress this, high decoherence that magnon has, and this is a big problem. And finally, what kind of propagating quantum states I can generate, okay, in reasonable nanostructures. And so there's many ways to answer this. I'm not giving an answer to all of these today, I'm sorry. I'm trying to start, we're starting to try to answer this. And again, from my experience working with different platforms, I know that it's very, very difficult to cover this whole map by a single degree of freedom alone, okay? So that's why hybrid quantum platforms exist. the solution is always to just bring something else, couple some degree of freedom that you can control to your system so you can really improve the functionality. And so I'm here to propose a hybrid platform that seems to work quite well. And this is a platform that couples spin waves in ferromagnets with paramagnetic spin ensembles, which for all of you in the audience, you can just think of this as MV centers. Okay, it's a bit more general, the theoretical treatment, but you can think of this as MV centers. Okay, so this is the outline of the talk. I'm going to talk to you first, just introduce the system, and on one slide try to summarize the theory of how we describe this. Then I'm going to show you how we can use the spin ensemble to control coherently the propagation of spin waves. Then I'm going to show you how we can use MVs to to detect magnum fluctuations with a different kind of scheme than relaxometry, which we have seen in other talks. And then I'm going to glide over other results and focus on talking what we are doing right now, which is answer this problem of the coherence. Okay, so what's the system we are considering? Well, thankfully, Tuno was nice enough to shift talks with me, so it's exactly the same system that Tuno has. Okay, so before I continue, if you are one of these people who care about whether something is quantum or not, I already, come clear. Nothing you're going to see right now is quantum. You're going to see density matrices and hats and operators just because I feel comfortable with quantum theory, and I hope that I will need this theory when I get to the quantum regime. But the results I'm going to show are not quantum. Okay. Anyway, so this is the system we're considering. It's basically kind of like a theoretical toy model of what Tuno just showed in his experiments. And actually Tuno is a part of this paper where we discuss this. So we consider a thin film for a magnetic field of YIG, and on top of inside of which spin waves can propagate. So there's different kind of bands of spin wave bands. I don't gonna bother with the details, but basically we can consider only the fundamental band. So still in the paper we consider all of them, but just say just a single band of spin waves. So spin wave eigenmodes are just labeled by their parallel wave vector. Okay. And then on top of this we have like a slab of diamond containing MV centers. Okay, and this is in principle a very simple system in terms of nanoengineering. Just randomly position MV centers and just independent. So there's relatively low density, so they don't talk to each other. And something very important, also, everybody has mentioned this, is the possibility of optical pumping of the MV centers. This is going to be very important. I'm going to do a spoiler now, so it will turn out, and you will see how that if you don't optically pump your MV centers, the MV centers do nothing to the magnons. The system is effectively uncoupled. And so for me as a theorist, this optical pumping works like this. So this is the ground state manifold of the MV centers. This is a 3-level system, and these two transitions will couple to the spin waves. But there's also, a huge other level structure in the optical domain. And for me, optical pumping is, a process by which you can just shine a laser and then pump occupation from the excited states down into the ground state. Okay, so basically, even at room temperature, I can just drive my MV center into its ground state or very close. Good. So how do we describe this theoretically? Again, this is going to be very fast, but if you're interested, you can go to the paper. This paper has 47 pages, so we really try to make an exhaustive study. But in a nutshell, what we do is we first just solve the eigenmodes and of the magnon eigenmodes from the classical equations, which allow us, and quantize them, which allow us to just basically write this very simple harmonic oscillator Hamiltonian. These operators are magnon operators. Then we just compute the coupling to MV centers, which is just magnetic dipole interaction of the magnetic dipole of the MV centers couples to the magnetic field generated by these spin waves. Again, in what I'm going to show now on this parameter regime, after a lot of rotating wave approximations, you can cast in the forms of typical James Cummings, where basically one of the two transitions of the MV center is weakly coupled and we can neglect it. So for the rest of this talk, I'm going to assume that this is just a 2-level system, okay? But again, in the paper we discuss going outside of this paradigm. And then we use our basic tool as quantum opticians. We just write a master equation to describe the whole system, okay? And this master equation describes the evolution of the density matrix of the whole system, okay? This is spin waves plus all the MVs, okay? And it contains just some coherent evolution, Hamiltonians of both components and their coupling, and a bunch of dissipative terms. This one is the magnon damping, which we describe just as coupling of magnons to a thermal bath. These two, dt1 and dt2, describe decay and dephasing of the MV center. And this thing contains a lot of terms, but in the end, it just describes the optical pumping, okay? So the procedure by which I can just drive population effectively from this state down to the ground state. Yeah, and then so what I'm going to do in the rest of the talk is showing you a couple of examples where instead of treating this whole master equation, I use relatively common techniques in open quantum systems to just trace out part of the Hilbert space. In particular, I will derive equations of master equation for the magnons only, which include the back action of the MV centers, and vice versa. And if you want to know how to do this in the spirit of a bit sharing between communities and also in the spirit of shameless self-advertising, you can just go to this tutorial, which I recently posted in arXiv, where I really go over all this, a practical implementation of all these techniques for deriving effective master equations in open quantum systems. Okay. So let's go to the results now. So the first thing I want to see is whether I can control spin waves by using the back action of this MV center ensemble. So what we, oops, sorry, this shouldn't be here. So what we do is we derive an equation for the magnon density matrix, including all the back action of this MV center ensemble. And we see that the effect that MV centers have is actually not very surprising. They induce a frequency shift to every magnon mode, and they induce a modification of the line width, of the bare line width of every magnon node. And so all these shifts can be calculated analytically. It's a bit long, but what is important is the dependence with the parameters here. So we have first the MV intensity, how many MVs I have per unit volume. So the more MVs I have, the stronger the effect. Makes sense. I have this Lorentzian factor here, which tells me that only magnons that are resonant with the MV transition within the line width of the MVs are going to be affected by the MVs. And then I have this minus sigma c, which is basically the difference between the populations of the excited state and the ground state of the MV center. Okay? And so something very nice that you can see from here is that you can really have external control over the effect of this bath on the spin waves. You can, for instance, optically pump the system. If the MV centers are in a thermal state at room temperature, this is very, very small because the occupations of excited and ground state are basically the same. If you pump it, you can increase this by 4 orders of magnitude. And this is the reason why when we just turn off our laser, you see that the effect of the spin of the MV centers actually disappears. Okay, something else I want to say. This is also a textbook result of quantum optics. We know that in a two-level system, there can never be just population inversion by driving, which means that this minus sigma c here is always going to be positive. Okay, so what I mean is that in this regime, in this regime, we are always increasing the line width of the magnons by the back action of the MV centers. However, I want to point out, I'm not going to get into details, but I want to point out that this is not always the case. And we have this theory paper where we study what happens in the regime of very strong driving of both the system and the spin bath. And you can see that in this regime, you can actually achieve a gamma that is not only negative, but that can overcome the bare line width so that you get net amplification in the system. And this model was actually used to reproduce some experiments by the group of Gerhard-Kirchmeier with superconducting microwave cavities. Okay, so again, we have some modification of the spin waves. What does this mean for the spin wave propagation? And so what I'm plotting here is for you is 3 observables or three quantities that characterize the propagation of spin waves. First is the dispersion relation, frequency versus wave vector, okay, along a particular direction. Then the group velocity, how fast do spin waves go, and then the propagation length, how far do they go before they decay. And so these boring black lines here are what happens when you are not turning on your laser. So MV centers are inert. They're not affecting the spin waves. Now, if we turn on the laser, all hell breaks loose, and we see a lot of effects. My favorite plot is the middle one. So you can see that here we have a 1,000-fold increase on the propagation velocity of the spin waves. We have also this very weird kind of region. This dashed line means the group velocity is negative. This means we're engineering a backward dispersion region where the group velocity and the phase velocity have opposite sign. And also we have this point here where negative becomes positive, which means we have completely stopped the spin waves. So the group velocity is 0, and you can also see in the propagation length that you get no propagation length. And this is an analog of, or it's related to the effect of slow light that we know in quantum optics. Good, so apart from these particular results, what I really like about these results is that we have a way to tune the coherent propagation of spin waves. And that we can do a lot of stuff with a very simple system. Okay, I'm just throwing a slab of randomly positioned MV centers and either turning a laser on or off. But we have plenty of ideas to refine this. For instance, you can think of now shining a laser with some spatial modulation into the MV ensemble in order to draw any kind of optical device for the spin waves. And we have ideas to draw beam splitters, mirrors, magnetic crystals, just by engineering spatially the back action of these MV centers. Okay, so let me go now to completely kind of like opposite paradigm, where now I want to see what is the effective dynamics of a single MV that is lying on top of a magnetic film. And again, we can calculate this using our tools, and we see, again, the same kind of effects. So the spin waves, what they do to the MV, first they modify these T1 and T2, the coherence times. This is the basis of all these relaxometry experiments that we saw in this conference. But what I want to talk about here is the second effect, which is the frequency shift. Okay, so the two-level transition of the MV center is a frequency shift, which we can calculate analytically. But the only important thing I want you to look at here is that this frequency depends on the NV film distance. Okay, and this makes sense because the magnetic fluctuations decrease as you go away from the film. This means we can think of other methods of trying to sense magnetic fluctuations of the spin waves. Of course, the first one is we can just try to measure this frequency shift by like tracking the microwave resonance of the MV centers. But I want to propose here an even maybe a bit more exotic one. And this relies on the fact that because we have a frequency shift that depends on the position, we're going to have a force. Okay, energy that depends on position gives you a force. So there's a mechanical force exerted on any MV center, and this means we can think of an experiment to transduce magnetic fluctuations into mechanical fluctuations of a resonator. We can think of something like this. This has been done in many labs. We can think of attaching a nanodiamond containing a certain number of MV centers to a macromechanical resonator and make use of the fact that there's a really good sensitivity for mechanical sensing of forces. Okay, so by transducing these fluctuations into a mechanical fluctuations, you can maybe gain sensing resolution. So what I'm plotting here is the force per single MV, okay, that it would experience as a function of the separation from the film, as in units of the thickness, which is in this case I think 200 nanometers. So what I want you to look at is this green line. Okay, this is the force that optically pumped single MV at room temperature will experience, and you see it's between 10 to the minus 18 and 10 to the minus 21 Newton, up to about 200 nanometers, which means that, and by the way, this gray area that I'm highlighting is more or less the resolution. The typical resolutions of most ultra-sensitive nanomechanical force detectors. So what this means is that if I go to about 200 nanometers from the surface with a single MV, I can already take the signal from the fluctuations of the field generated by the spin waves. But even cooler from my side is that if you look at the orange line, which represents basically the ground state, so this is at 0.1 Kelvin, and you consider that instead of having one MV, you can have a diamond with like 1,000 MVs, then this goes up, this dashed line will go up into the resolution zone, which means that, in principle, it should be possible to measure with this mechanical sensing the spin wave fluctuations down to the ground state, which would allow us, in principle, to resolve the signal of a single magnon. Okay, so I don't know how much time I have. 2 minutes. Okay, then I'm going to glide very fast about other results that might be useful for you. So first, we also show that spin waves do not, so that MV centers can also really burn holes in the magnetic field fluctuations below the film, which means that you can even really reduce the noise floor. So in principle, this we want to explore if this can enhance the signal-to-noise ratio in detecting these magnetic fluctuations. We also saw, and this is not a surprise, that magnons can, of course, mediate coupling between qubits, and that this coupling is strongly non-reciprocal. So, for instance, here I'm showing one qubit is here, and then as a function of the position of the other qubit was the coupling rate, and you can see that couplings to the right will couple, qubits to the right will couple, qubits to the left will not. This is also not surprising because the spin waves are highly non-reciprocal. But again, so going back to my map to kind of conclude, so I still cannot claim to have a satisfactory answer to all of these points. I think from our results with this platform, there is hope, and there should be quotes unquote in these tick marks, but I think there is hope that we can at least fulfill these kind of these three requirements, even though there's still a lot of work to do. Okay, so we know that it is possible to mediate coupling, for instance, between qubits, but we don't know if this is useful yet. Okay, there's still a lot of work to do. We have to explore new platforms, we have to tune it, and we have to see how far we can go. And in the last 1 minute, I'm going to just tell you that what we are doing right now is try to answer these two, okay, which now have to do with the coherence, and means that we have to really address the elephant in the room. Okay, we need to understand the coherence, and by we I mean not only our team. I hope this is a call to action for all of you. I think we cannot really think of quantum magnetics experiments if we don't understand the coherence of magnets. And so, okay, so I glide through the problem, but basically what we're doing right now, many people is doing, is quantizing from the classical dynamical equations. But we know that if we started with a more microscopic picture of magnon coupled to all the degrees of freedom that induce the coherence, for instance, phonons, spin impurities, and all that we know, we could derive a master equation for this, which in principle could be different from this one, even though, of course, they should recover the same classical limit, okay? And these terms that are responsible for the coherence, for instance, the phasing, or we don't know actually, are really important to evaluate, okay? So our plan of action now, our goal is to do exactly the same kind of treatment I did for the MV center and magnon. I want to start with a very extended model, including all these degrees of freedom, and then tracing them out and derive this master equation to get an analytical expression for the coherent rate, which means that if I have this analytical expression, I can now do all what we know from nanophotonics, nanostructure engineering, and explore how we can really suppress this decoherence. And so my last slide, just to show you that this is possible, and just very, very preliminary results. This is the work from my colleague Marco, who just started a PhD, and he has been calculating the phonon contribution to magnon line width, which he plots here, for a Higgs sphere, okay, as a function of magnetic field. Okay, so this is very small sizes. Marco is working now into extending it to up to 1 millimeter, but what you can see here is, as you move the magnetic field, you're scanning the magnon frequency, and every time you hit one phonon resonance, you have a high peak, so they couple strongly, you have a strong dissipation. But even better, every time you lie, let's look at the orange line, for instance, every time you lie here in between two phonon resonances, you are detuned from any phonons, okay? You are in an effective band gap that is created by the fact that the phonon structure of a sphere is discrete, and then you have a strong suppression. So what we are seeing here is basically a Purcell suppression of the line width or the decay rate of a magnon. And so for me, this is very hopeful because it means, or it indicates that really it is possible to tune the line width so that Gilbert damping or magnon damping is not a fundamental property, and they can be engineered. And my goal, our goal for the next year is to try to answer how far can we suppress it, which of course is super relevant for quantum experiments. And with this, I just thank you. So I thank my two collaborators, Tuno and Oriol, collaborating in the spin magnon platform, and I thank you for your attention.